Hi everybody, and welcome back to Lecture 3 of Digital Integrated Circuits. Now we get to our last part of the lecture, which is leakage in nanoscaled transistors. So, as we can see here, transistors that are supposed to be off actually leak. We have our VGS versus IDS curve, which we looked at, and it always looks like this. And we usually take whatever point is our VT over here, and we say that the transistor is off when it's below VT. But actually, this is non-zero. In fact, it's actually pretty big. Another thing I just want to point out is that when we look at leakage, we should always look at the off transistors. So if we take a CMOS inverter here, and one of them has 0 at the input and the other has VDD at the input, well, let's start with the top one. When we have 0 at the input, we have this bottom NMOS which is off and the top PMOS which is on. And we're only talking about the leakage as the current that's running through the NMOS. Why do I say that? Because we have our output capacitance here, and it's actually in this case loaded up with charge, and so we have a VDD voltage here. If for some reason we lose some of the voltage and we have some sort of VDD minus some sort of delta V over here, then immediately what will happen is the PMOS will replenish this with extra current. We can see that looking at a standard VDS to ID curve. When we have our curve is something like this on the PMOS, in this case, why do we not have any current here in the steady state? Because we're over at this point where VDS or VSD of the PMOS is 0. The minute that a little bit of charge leaks away, and then we have something like a VDD minus delta over here, so we're actually the VSD on the PMOS is larger than that, and we have a non-zero current which will run through here. This is the on state of the transistor. It's not leakage. On the other hand, this transistor is supposed to be off where it's sub-threshold. Our VGS is 0 volts, right, which is smaller than VT, and therefore this is not supposed to be having any current through it. Any current that runs through here is our leakage. So whenever we're analyzing a circuit and we want to see the sub-threshold leakage currents that leak, we should find out which transistors are off. In the case of our same inverter with VDD at the input, now the PMOS is off, the NMOS is on. Again, the NMOS is on, so it's working according to this graph, and the reason it has 0 current is because we have our VDS is 0 at this point. But the second that we get some sort of delta here, then we'll be somewhere over here and we'll get immediate current that discharges the output. So the leakage is only the current that's actually running through the PMOS. So before we start and detailing each and every type of the leakage that we were going to discuss, we should look at a starting overview of the leakages in a MOS transistor. So here we have an NMOS type transistor with a source, drain, an oxide, and a polysilicon gate. And we'll look at the first type, and the main type of leakage that we're going to discuss is the subthreshold leakage. Subthreshold leakage is leakage that runs from the drain to the source or source to the drain through the channel of the transistor, but it is when there is no channel or when VGS is smaller than VT. Okay, we will see in the next few slides that subthreshold leakage is proportional to the exponent of VGS minus VT. So it's both exponentially dependent on VGS and on our threshold voltage of our transistor. We also discussed the fact that we have this Dibble current, this drain-induced barrier lowering. And Dibble can be looked at in several ways. One of them is that VT goes lower, so it could actually be inside this I subthreshold type of proportionality, or it could be just shown that there's an increase in the leakage depending on VDS. So in any case, due to Dibble, we have an exponential dependence on the VDS of the transistor. Again, both of these are leakage from the drain to the source or source to the drain through the channel of the transistor, and they're exponentially dependent on VGS, VT, and VDS. The second type of leakage that we're going to be looking at is the gate leakage. Gate leakage is actually tunneling through the oxide. So we have this oxide here, which is supposed to be some sort of capacitance, some sort of open circuit, some sort of high resistance, and there isn't supposed to be any current through it. But there is some tunneling, which can actually grow larger, and there's more tunneling the thinner the oxide is. So this is the T-ox of this. So we're proportional to 1 divided by T-ox, and it is also dependent on the actual voltage drop over the gate. Now, the question is, where does this gate leakage go? And it either goes into the substrate, as we can see here, if there's no channel, or if there's a channel, it actually goes either to the source or drain, or to both of them if there's a channel here. So that is the direction of the gate leakage. There are also leakage components that go on the overlap regions over here. This is called edge direct tunneling, where we have leakage between the gate and the diffusion on the two sides. The next leakage we have is called JIDL, or gate-induced drain leakage. And gate-induced drain leakage is leakage that we'll see that is due to either a high field in the overlap region between the gate and drain, or due to band-to-band tunneling. But in any case, it's leakage that goes from the drain to the substrate in this direction. Similarly, we have reverse diode leakage. So we have two diodes here. We have the source diode and the drain diode to the substrate, and these are reverse bias diodes, and so they have some reverse bias leakage. Finally, we have something that's not exactly a leakage, but rather a fault of the transistor due to a type of a leakage current, and we call it punch-through. And that's when the diffusion layers of the drain and the source actually merge together, and then we have free-running current between the drain and the source that is not controlled by the gate as it should be. So now let's go into detail, and we'll start with subthreshold leakage, which as I mentioned before, is our most important leakage, and it's the one we'll discuss in most detail. Okay, so as usual, there are many different ways to look at and describe these different phenomena, and I'll mention a few of the ones that are commonly used. So basically, one of them is that when VGS is smaller than VT, there is still a finite carrier concentration at the surface. So generally, we said that when we're in accumulation, we have very few, if this is in a p-type substrate, we have very few electrons at the surface of the semiconductor. These are, of course, the minority carriers, and it's a p-type implant here in the channel, so there's very few carriers, but there are carriers. And if there are carriers and we have a voltage drop across the drain and source, then these carriers can actually run through, and that is our leakage. Furthermore, as we raise the voltage on the gate, we're actually starting to bend the bands, and as we bend the bands, we start to accumulate more and more charge on the surface. We may not have hit inversion, where the number of minority carriers is the same as the number of majority carriers used to be, but we still have this more and more carriers that start to accumulate here as we apply voltage. This is known as weak inversion, okay? And it means that, again, we have some minority carriers, or some concentration of minority carriers, which do cause current, but it's not enough to cause a large current, which happens at our threshold voltage. So that's one way to look at it. Another way to look at it is it's as if we have a BJT that's not exactly closed. There are different ways to look at this type of a reason for subthreshold leakage. Okay. The thing is that the amount of carriers at the surface is proportional to the exponent of the surface potential divided by the thermal voltage, and therefore we get our subthreshold current is proportional to VGS minus VT divided by N times the thermal voltage, and we'll discuss in a second what this VGS minus VT divided by N is, but it's the amount of inversion that we've reached. Okay, so what is N? Well, we discussed N before. We saw that as similar to we saw with the body effect, due to multi-channel capacitance, the surface voltage isn't only controlled by the gate. It's also controlled by the back gate, or by other terminals here that have some sort of a capacitance, some sort of transfer function to the surface potential. Okay, and we said that we called this the change of the surface potential according to our change in the gate potential, which is what we wanted to have. We wanted to control completely our surface by here, but we saw it's not exactly, because we have some other terminals, especially the bulk terminal, which is having some of the grip on the surface potential. So the amount of control we have is the C oxy divided by C oxy plus C depletion, and that's 1 over N. Okay, so N is finally, its definition is 1 plus C depletion over C oxy, and that's the same N that we have over here in the amount, and we'll see what we do with that in a second. Okay, so let's make this a bit easier. Remember that our subthreshold current is some sort of a constant times the size of the transistor, W over L, times, again, we have this exponential dependence on VGS minus VT over NVT that we can either look at as the amount of charge we have there or as like a parasitic BJT that we have when we're in weak inversion. Okay, we've defined the threshold voltage according to the current. So we saw before that one of our ways to find threshold voltage, we said for both VT lin and VT sat, is we take our VGS to ID curve and we say, okay, we have 100 nanoamps times W over L, and when we reach this point, this is what we call VT. So that was a definition. So IDS at VGS equals VT at this point is equal to 100 nanometers times W over L. Well, we know that if we now are going to substitute and put here instead of VGS, we're going to put VT, it has to be equal to 100 nanoamps times L. So the subthreshold current when VGS equals VT is going to be this constant times W over L times e to the power of 0 divided by n VT, which is just 1. So it's just going to be this constant times W over L, and that has to be, according to the boundary conditions, equal to 100 nanoamps times W over L, which are going to cross off, and our constant is going to just be 100 nanoamps. So we can model our subthreshold current and say that subthreshold current in nanoamps is just 100 W over L e to the power of VGS minus VT over NVT. Okay, let's take that. That's a simple way of writing down our subthreshold current. And now we're going to apply a log to this IDS curve. So we had, our IDS curve that we know really well, this VGS to ID, which looks like this, but we can't see much in this area. So what we're going to do is we're going to apply a log to this y-axis, and then our exponents we're going to turn into linear areas, and we're going to get a curve that looks kind of like this. Okay, so we said that VT is going to be this point where we have 100 times W over L nanoamps, and under that we're going to have an exponential area, so it's going to be pretty much linear. The slope of this is going to be 1 over S, where S is what we call the subthreshold slope, because it's the slope of this log IDS to VGS curve in the subthreshold area. Okay, we don't like to talk about the 1 over S. We like to talk about the inverse of it, which we will call the subthreshold swing. So S is going to be known as the subthreshold swing. And S is defined as ln 10 of KT to Q, which is VT, 1 plus C dep over C ox, which is N, or if we take this constant, it's going to be 2.3 N times Vt. Remember, Vt equals 26 millivolts at room temperature. Okay, so that's going to be the definition of S, and then we can rewrite our model before. So if the subthreshold current was in nanoamps was 100 W over L e to the power of VGS minus VT over NVT, we can then substitute with S, and we get rid of the E, and it becomes a 10 to the power of, so we get 100 W over L 10 to the power of VGS minus VT over our new parameter S, which replaced our NVT that was there before. That is our subthreshold current, and we usually in digital circuits are discussing levels of 0 or 1. So most of our transistors that are going to be off are going to have a 0 at their input, at their gate, and therefore we can call VGS equals 0 the off current. So when we say I off, we mean it's when VGS equals 0, and then we just plug in VGS equals 0 to this model over here, and we say I off in nanoamps is 100 W over L 10 to the power minus VT over S. Okay, so what we found out from this is that subthreshold leakage is, first of all, exponentially dependent on VT. Second of all, it's exponentially, on VGS, except also exponentially dependent on VT, because we had VGS minus VT in our exponent. And this is very important because that means that the closer we are to VT, the more leakage we're going to get, but also different things that cause variation, either processing, which is because of RDF and so forth, we're going to get a lower or a higher VT, or due to temperature, VT is going to change. It's going to exponentially affect the amount of leakage that we're going to have. Okay, and S, we defined it as the subthreshold swing coefficient. Now, why did we define it like that? It's actually, S is given in the metric of millivolts to decades. So what does that mean? It actually means how much we move along this x-axis, which is in volts, right? So this is in millivolts. How many millivolts we have to move along this x-axis to actually change decades in the y-axis. Okay, so as you see, since this is a logarithmic scale, this is 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, etc. And when we say our optimal S comes out, as we can see here. If we do NFT ln 10, if n equals 1, it comes out 60. So, or 60 millivolts. Okay, so that's the optimal S we can get. Our optimal subthreshold swing is 60 millivolts per decade. That means that if we move 60 millivolts under VT, what it's going to do, it's going to cause our voltage to go down 1 decade. Okay, or times 10, right? 120 millivolts, we're going to go down 2 decades, and so forth. That means that if we would want to make a change where, for example, we would want to close our transistor such that our off current is like four orders of magnitude smaller than our on current, we would need to move 4 S's, or 240 millivolts in the optimal case. Unfortunately, a realistic transistor, or at least a realistic planar transistor, usually has an S that's more around 100. And then to move our, to get 4 orders of magnitude less leakage current than we had on current, we need at least 400 millivolts of swing. Okay, again, the S is a factor of n, so if is a function of n. If n is equal to 1, which is the optimal n, we get S that equals 60. If it's not, if it's more realistic, we get something closer to 100. In fact, one of the reasons that we make newer devices is to try to improve that subthreshold swing. Okay, so let's look at just a short example, kind of what I said before. We want to design a transistor. If we're now a device designer and we want to design a transistor, and we want to make sure that we have this I-on to I-off ratio, and it has to be at least 10 to the 4th. So we remember that I-on means that VGS is bigger than VT, right? So let's take the smallest amount we can have there, and let's say the VGS is exactly equal to VT, and we want to have I-off. I-off means that VGS equals 0. So we want to have that our on current over our off current is at least going to be 4 orders of magnitude, okay? On the other hand, we have a perfect transistor here, and it has 60 millivolts per decade and of subthreshold swing, and I want to know what the minimum VT is. So that means that at VT, we can go now 4 decades down to get to 0. So starting at 0, going 4 decades to the right, if each one of them is 60 millivolts, we're going to arrive at 240 millivolts. And that has to be, that is our minimum VT. So minimum VT would be 240 millivolts. If our S was equal to 100, as we said before, millivolts per decade, then our minimum VT would have to be 400 millivolts in this case. That we wanted 4 orders of magnitude I-on to I-off ratio. So that was discussing subthreshold leakage dependence on basically VGS and VT, but we said we also have Dibble. Dibble, we said, is a drain-induced barrier lowering, and it's an exponential increase in subthreshold leakage due to VDS. And we can see that in these types of graphs. So again, this graph is just the same VGS to ID. Or looking at the other way, this is VSG, or the negative VGS, which is for a PMOS. So these are PMOS transistors, these are NMOS transistors. And the curves we see here, this again is, it's not ID, it's log ID. The curves we have here, the black one is at 50 millivolts, and the blue one is at 1.2 volts. So this is basically in saturation, and this is basically in linear. And what we see is there's a difference in the current we get between the leakage current we get over here, and this difference is again due to Dibble. Okay, So that is kind of what we see from our Dibble current. One of the popular models for subthreshold current takes this into effect. So we take I subthreshold is some sort of a constant, e to the power of VGS minus VT over NVT. That's the exponential dependence on VGS and VT with our subthreshold coefficient inside that, and our temperature dependence in the thermal voltage. Okay, and then we have this times e to the power of eta VDS over NVT, where eta is the Dibble coefficient. This middle part tries to take into account what happens when, for example, VDS is 0. This just cancels out the whole thing, so we get no leakage, obviously, if VDS is 0. So this is one of the popular models for subthreshold current. Other popular models for subthreshold current are the EKV model, and there are several others that try to model it in a nice way. So what about subthreshold dependence on temperature? It's actually quite complex. So remember that as temperature goes up, mobility degrades. What we said happens is that we want to have ballistic movement of our electron across the channel, but then we have these atoms all over the place inside the channel, and the atoms, they move, and the amount of energy they have makes them move more. So the more and more they move, the more and more probability that this electron's going to hit them and take a longer time to go actually across the channel, and that is a degradation of the mobility. So as temperature goes up, mobility goes down, right? But mobility isn't that important to us when we talk about leakage, because anyway the electrons aren't going very fast and so forth. And we have other device parameters such as flat band voltage that are temperature dependent, and VT, which is temperature dependent. So if we actually take them all to account and run simulations or tests, what we'll see is that subthreshold leakage actually rises exponentially with temperature. That's without considering temperature inversion, but temperature inversion isn't as important, again, for leakage, as we'll see in a moment. So the subthreshold current is e to the power of VGS minus VT over NVT. We have a dependence of temperature here. We have a dependence of temperature here. And what comes out in the end is that we get this exponential rise of subthreshold leakage at temperature. So when we want to test something for high leakage, we test it at a high temperature. And that takes me again, I mentioned on the previous slide, temperature inversion. And this is not necessarily talking about leakage, but temperature inversion in general. I thought this was a good place to discuss it within our slides. So the classic approach to temperature is how it affects delay. So again, we're talking about our on current, and the current we have is proportional to the mobility, and mobility is reverse or inversely proportional to temperature. And when we do that, it means that the propagation delay is proportional to temperature. In other words, as the temperature rises, so does the propagation delay, and our speed decreases. So speed decreases in temperature. That is, again, discussing on current, not discussing our off current necessarily, but that's our traditional approach to temperature dependence of delay. Okay, but we have something else. VT decreases by as much as 3 millivolts per degree of Celsius. So if VT decreases, let's see what happens. VT, we said now, is inversely proportional to temperature, and TPD, of course, is proportional to VT. The higher the VT, the slower we get. Okay, so when we put that together, we see that TPD is inversely proportional to temperature. So speed actually increases with temperature. So this and this contradict each other, right? Okay, so what do we do with that? Actually, the point of temperature inversion is the voltage at which the speed increases with temperature, which is about 1 volt VDD. So remember that our current is going to be proportional to a VGS minus VT. And of course, that's going to be like equal to VDD minus VT for most digital things. So the amount that we're dependent on VT, it increases as the actual difference between these go down, or as VDD goes down. So when we changed our supply rails, and when they were very high at 5 volts or whatever, this part was negligible, and this completely dominated. But as we went down and we got around 1 volt, this actually becomes dominant over this. That's called the temperature inversion point. And when we're at temperature inversion point, we have to use a high temperature for fast circuits and a low fast corners, and a low temperature for slow corners. Okay, back to our leakages, and we finished discussing subthreshold leakage for now. Let's discuss gate leakage. So there are two main mechanisms that cause gate leakage. One is called direct tunneling, and this is the dominant leakage. And there's also Fowler-Nordheim tunneling, which is very popular in like the operation of flash devices. Okay, so of course the gate leakage is exponentially dependent on the gate voltage, VG, and the oxide thickness. There's some of the models, or like one of the models is over here, and you can see that the dependence on the oxide thickness, Tox, and on the gate voltage, VG or VDD in this case. Okay, it is very it's not very dependent on temperature, and that can be exploited as us by circuit designers. Again, what I told you before is that we have our main gate leakage is to whatever is under the gate, if it's going to be the substrate when there's no channel, or the channel, which will then be probably divided between the source and the drain if there is a channel, or there's also some direct components of the gate leakage which go directly to the source or directly to the drain in the areas of overlap between them. An interesting thing about gate leakage is it's much stronger in NMOS transistors than PMOS transistors. The barrier for holes is higher, and this again can be exploited. And the third thing is that the minimum oxide thickness is about 1.2 nanometers. Under that, this barrier is just not enough to block the passage of electrons, and everything will just jump over the barrier. So really the kind of hard minimum, and what almost was at some point was considered what was going to kill Moore's law, was this thickness of the oxide, which would possibly get which arrived at 1.2 nanometers and couldn't be scaled anymore. Okay, our next leakage component is the gate-induced drain leakage, or JIDL. Okay, JIDL current flows from the drain to the substrate, and what is it exactly? So actually, when we look at at this VGS versus the log ID type of a thing, what we could imagine is that if we took our gate voltage, and instead of having VGS stop at 0, we could continue it, and essentially we would eventually get to the fact that we had have 0, or even some sort of a reverse type of a current, right? But that doesn't happen. Actually, if we take this, we see that at some point the current starts rising, and the rise is usually due to this JIDL. So JIDL's two main phenomena are as such. In the area of overlap between the gate and the drain, since we have now some sort of a high voltage difference, so we have VG over here and we have VD over here, and the VD is high, right? We get this large voltage VDG over the gate and drain. It causes a large field underneath and causes this creation of electron hole pairs, and then they cause leakage to the drain, to the bulk. Another option is what's called band-to-band tunneling, which is where, as we can see in our regular type of gate to drain type of a band difference, what we have is this drop here due to the difference in the two types of dopings. But once we put our drain voltage on here, we cause these bands to again go much lower. Okay, and since we have this really steep type of a change over here in the bands from the gate to the drain, we have an area where the valence and the conduction bands are very close together, and then electrons can essentially just jump over this barrier and tunnel through. That's called band-to-band tunneling. It gets worse the higher our differences. So usually we have our maximum drain voltage to be VDD and our minimum gate voltage to be 0. So our maximum voltage difference is VDD over here, but sometimes we can actually apply some negative gate voltage, and then it gets even worse until we start getting more and more of this type of a leakage. And again, this leakage is caused by the gate voltage, or the difference between the gate and the drain voltage, but the direction of the leakage is from the drain to the substrate. A similar phenomenon is diode leakage. So if we have our MOSFET, which has the source, which is an N plus, and then a P sub, and then we have the drain is also an N plus, right? We have these two diodes. So we have a diode here and a diode here, and we made sure that these diodes were going to be reverse biased. Well, looking at our classic diode curve, we have our forward region, which is where our diode conducts, and then we have, as we go to a reverse bias, we go under the threshold, or like the 0.5 or 0.7 volts of the diode. It's not supposed to conduct. But as we go back, we see that there is a reverse leakage current that's non-zero, and that we get over here too. So again, that's from these diffusions, either from the drain or from the source down to the substrate. The density is 10 to 100 picoamps per square microns at 25 degrees for an older technology, 250 nanometer CMOS, and the current density doubles for every 9 degrees of Celsius, so it's very temperature dependent. Another thing about the diode leakage, well, it depends on the size of these diffusions. So if you remember, we can draw our transistor. A transistor can have some sort of a W and some sort of L like this, but in fact we could go and continue our diffusion like that, and we'd have all of this would be the same sort of potential. It wouldn't change the size of the transistor, it's still W over L, but the area of the diode is much bigger, causing many more paths for this type of a diode leakage into the substrate. Okay. Anyway, in deep submicron technologies, the diode leakage has become quite negligible in comparison to subthreshold leakage. Okay. And it's the same direction as JITL, so it's kind of hard to differentiate between them. Punch-through current. Okay, so finally, as VDS grows, right, we have our drain here, which has its depletion region. We have our source here, which has its depletion region. And as we add more and more voltage here, our depletion region grows. If we also reduce our the size of our the length of our channel, then this depletion region can actually merge with the depletion region of the source, and then we just have a free channel to actually punch the current through from the source to the drain, and that is not something that is a real transistor. Our transistor is supposed to be have the gate be the only control terminal, and it's not supposed to be able to have free running carriers from the source to the drain. So punch through is something that's not exactly a leakage. It's actually detrimental, and it can't be there, and we have to fix it and not allow it to happen. So as a summary for our leakages, and we have the little schematic we had from the first page over here, and here's a graph of again VGS versus log ID that kind of summarizes the different types of leakages. So subthreshold leakage, when IDS is large, it means that IDS is going to be larger than 0 when VGS is smaller than VT, which we wanted it to be 0. And this is due to weak inversion. It grows with VGS, VDS, and lower VTs. Okay, we have gate leakage, which means that the gate current is larger than 0, and this is due to direct tunneling through the oxide. It grows with the gate to body or gate to channel voltage and the oxide thickness. Gate-induced drain leakage, or JITL, is that we have a drain to body leakage due to higher electric fields in the GD overlap region of the drain, and it's dependent on VGD. Reversed biased diode leakage, that's again from both the drain and the source diffusions down to the body, and it's due to diffusion and thermal generation. And finally, we have punch through, which is again a drain to source leakage due to the depletion layers touching each other. So having that said, let's revisit our process corners. Do we have to redefine our PVT settings? So this is what we reached before. For the fast corner, we took a lower VT, a lower length, a lower T oxide, a higher voltage, and a lower temperature. And for the slow corner, we took exactly the opposite. Well, what about a max leakage corner? So let's see. VT, obviously for a max leakage corner, we want to take a low VT. It will cause more and more leakage. The lower VT is, the more leakage we get. Okay. For the L, again, we're going to take a lower L. The shorter the channel, the more leakage we're going to get. In fact, more short channel effects and so forth as well. Okay, how about oxide thickness? Well, oxide thickness, that's a question. The smaller the oxide thickness, actually, the better control from the gate to the channel is, and therefore it would actually suppress subthreshold leakage. But then again, the lower the oxide thickness, the more gate leakage we're going to get. So we can take either high or low depending on how we decide to define our corner. And for VDD, well, obviously the higher the voltage, we're going to get more leakages, so we'll take a high VDD. And for temperature, again, what we're going to do is we're going to take a high temperature, because high temperature causes VT to lower, and so forth. We said there's an exponential increase of subthreshold current due to high temperature. But what about temperature inversion, which we discussed before? Well, temperature inversion isn't going to have as much impact on our leakage corner, but it for sure is going to have an impact on our conductance corner. So both for the fast and the slow corner, we're going to have to reconsider if we have temperature inversion. For a fast corner now, actually the high temperature is going to be fast. In a slow corner, actually the low corner is going to be fast. So we're going to I lost my animation there. We're gonna turn around our little arrows, and we're gonna change them around. Actually, what's often done, because we're working close to the temperature inversion point, is we're going to test our fast corners at both low temperature and a high temperature, and our slow corner at both a low and a high temperature. So that was actually the end of lecture 3, and here's a long list of further reading, and we'll continue on with lecture 4, which will discuss design metrics.